Hello again. In this video, we're going to go over some of the different notations that we have for the derivative. Now, in a previous video, we saw that one way of denoting the derivative of f of x is just to put a prime next to f. So f prime evaluated at x is one way of denoting the derivative of f of x. But there are other ways of denoting the derivative of a function. For example, you can also denote the derivative using this notation, dy over dx. Now I want to show you where this comes from, where this notation comes from, by looking at this diagram here. Now in this diagram, suppose we have the graph of some function f of x that looks like this. And let's say we pick out 2 points on this function. Okay, so this point P is located at x comma f of x. And then we're going to pick another x value that's a little bit larger than this one. And we're going to call it x plus delta x. Now delta stands for a change in some quantity. So delta x is a change in x. So starting with this x here, if we make this change in x, delta x, this much change in x, then that will be at this point here, x plus delta x. So then this ordered pair here at q would be x plus delta x, comma, f evaluated at x plus delta x. Okay, and then let's draw the line, the secant line that goes through those 2 points. And then let's find the slope of that secant line. Of course, the slope of that secant line would be rise over run. The rise in this case would be this y value minus this y value. So f evaluated at x plus delta x minus f evaluated at x, right? It's the change in the y value here. And we're going to denote that by delta y, the change in y. So that's your rise. And then your run, of course, is just delta x. So one way of writing the slope of the secant line is to just say it's delta y divided by delta x. Essentially, it's rise over run, right? This is your delta y, and this is your delta x. Now, to find the slope of the tangent line at point P, at this point P, what we did before is we looked at the secant lines here as this point began to get closer and closer to x. In other words, as delta x approaches 0. This distance here approaches 0. And so you can see the secant lines as delta x is going towards 0 are approaching that tangent line at P. And of course the slopes of the secant lines are also approaching the slope of this tangent line. Okay, so the slope of the tangent line at P, which is the derivative of the function f of x, which we can denote as f prime of x, that's equal to the limit as delta x goes to 0 of delta y divided by delta x, because delta y over delta x is the slope of the secant lines. And the slope of the tangent line is the limit as delta x goes to 0 of the slopes of the secant lines, which can be written as delta y divided by delta x. And so we're going to write this limit in a more compact way. Instead of having to write out all of this, we're going to define that, or we're going to call it dy divided by dx. So dy divided by dx is defined to be this limit. And so it gives us a shorthand way of writing this limit out. But note that this limit is the derivative of f of x, because it's the slope of the tangent line at any point x. Okay, so that's another way of denoting the derivative, dy divided by dx. This is a reminder, this kind of notation is a reminder that it's the limit of delta y divided by delta x as delta x approaches 0. Okay, so we have two ways of denoting a derivative. We can also write the derivative as df divided by dx, and that's very similar to this. Instead of calling the output variable y, you're calling the output variable f. So that's really the same kind of notation. You can also write it like this. This is called the derivative operator. The d divided by the dx, that's called a derivative operator, and it operates on functions. So in this case, it's operating on whatever's in the parentheses next to it. So the way you would read this notation is this means the derivative of this function, and we say with respect to x. So it gives us the instantaneous rate of change in the function as x changes. A shorthand way of writing this derivative operator is to just write the capital D with a subscript x. And so this d divided by dx can be written more compactly as just capital D with a subscript x. So this is just the derivative operator written in a different way. And it means the same thing. It means you're taking the derivative of whatever's in parentheses next to it with respect to x. So this just means the derivative of f with respect to x, which is what this means as well. Df divided by dx really means the derivative of f with respect to x. So the derivative operator is operating on f, just like it is here. And then, of course, another way you could write this is as y prime. So if y is a function of x, then y prime would be the derivative of that function with respect to x. And then if you want to evaluate the derivative at a fixed number a, then using the prime notation, you would just say f prime evaluated at a, or y prime evaluated at a. If you use this notation, which is called Leibniz's notation, then what we do is we say df divided by dx, which is the derivative of f with respect to x. But then if you're going to evaluate that derivative at a fixed number a, then we draw a line next to it and we say x is equal to a. Okay, so this is just the derivative of f evaluated at x is equal to a. Okay, and this is the derivative of y with respect to x evaluated at x equal to a. Okay, so I just want to do a couple of examples where we find the derivatives of certain functions. So let's find the derivative of the square root of x function. And then we'll find an equation of the line tangent to the graph of f at the point 4, 2. Okay, so let's find the derivative of this function. Now remember, the definition of the derivative of f of x is a limit. It's the limit as h goes to 0 of f evaluated at x plus h minus f evaluated at x, all divided by h. Okay, so let's start with this. So I'm evaluating this function at this number x plus h. And so what's going to come out when I plug this into the function? Well, what this function does is it, to any number that you plug into it, what it does is it takes the square root of it. So if I put in a 4, f of 4 would be the square root of 4. If I put in x plus h, then it's just going to take the square root of that number. So we're going to get square root of x plus h out. Okay, and then minus f of x, which is just the square root of x, all over h. And then we have to find the limit of this as h goes to 0. Now, initially, if you try to evaluate this limit using direct substitution, when you plug 0 in for h, notice that you get square root of x minus the square root of x on top, which is 0. And then on the bottom, when you plug 0 in for h, of course, you get 0 there as well. So this has an indeterminate form of 0 over 0. And so we need to change the form and make it determinable. And so what we're going to do to make this determinable is multiply by the conjugate of this top piece. Okay, so I'm going to multiply by the conjugate of this, which happens to be the square root of x plus h plus the square root of x. Remember, in the conjugate, you change the sign of one of these two terms. So I'm going to change this one to a plus sign. Of course, I have to multiply the bottom by this as well, because I have to multiply by 1. And then let's go ahead and FOIL the top out. So the first would be this times this. Now, when you multiply a square root by the same square root, the square roots cancel out, and you're left with what's inside the square root. So in this case, you're left with x plus h. And then notice here you get this square root times the square root of x, and it's a plus. But then you get the same thing when you multiply the inners together. You get this square root of x times this square root of x plus h. But now this one has a minus sign in front. And so the middle term cancels out because the outer has a plus sign, square root of x times square root of x plus h, and the inner is a minus sign, square root of x times the square root of x plus h. So that middle term cancels out. And then the last would be the square root of negative square root of x times positive square root of x. And again, the square roots cancel, and you're just left with x, except it has a minus sign in front. So that's just minus x. Okay, and then on the bottom, I'm not going to FOIL this out. It's just h times this. Okay, and then we have to find the limit of this as h goes to 0. Okay, so then let's try to evaluate this using substitution. Now notice these x's cancel, and then you're left with h over h at that point, and so the h's cancel. Okay, so these h's cancel. When the h's cancel, you're left with 1 over 1. So remember, there's a 1 on top here. And now when we try to evaluate this limit using substitution and we plug 0 in for this h, this is getting closer to the square root of x as h gets closer to 0, plus this other square root of x. So overall, this limit is getting closer to 1 over the square root of x plus the square root of x, which of course is 2 square roots of x. Okay, so that's our limit. The limit is 1 over 2 times the square root of x. Okay, and that's the derivative of this function. Now, this function, the derivative, describes the slope of the tangent line to this function at any point x. It also describes the instantaneous rate of change in this function x at any point. And so we're going to use that it also describes the slope of the tangent line at any point x. Okay, and we're going to use that to find the equation of the tangent line at this point 4, 2. Okay, so let's find that for part B. And by the way, you can write this derivative as dy dx as well, right? That's an alternative notation for the derivative. Or you could just write it as f prime of x. But regardless of how you write it, it does give us the slope of the tangent line at any point x. Okay, and we're going to use that to find the equation of the tangent line at the point 4, 2. Okay, so let's find the slope first of the tangent line at this particular point. And so I just have to plug a 4 into this derivative to find it. So f prime evaluated at 4, and that'll give me the slope of the tangent line when x is equal to 4. Okay, and so you get 1 over 2 times the square root of 4, which is just 1 over 2 times 2, right? 1/4. And we know it goes to this point 4, 2, so we can use the point slope formula to find the equation of the tangent line. Okay, so m is 1/4, and then x1 is 4, and y1 is 2. Okay, and then let's just distribute the 1/4. So you get 1/4 x minus 1, and then add this 2 to both sides. And so you get 1/4 x plus 1. Okay, and so that's the equation of the tangent line at this particular point. Okay. So let's look at one more. Okay. By the way, the graph of this, so the graph of this function square root of x, the graph looks like this. And then we're trying to find the equation of the tangent line at 4, 2, which is at this point here. And so that's what the equation, or that's what the tangent line looks like. And you can see the equation kind of matches that. This does have a positive slope, so it looks to be about 1/4. And it has a y-intercept of 1. So this equation appears to be matching our graph. Okay, so let's look at one more. Let's find the derivative of this function, 1 over t squared. Okay, so let's go back to the definition of a derivative. So it's the limit as h goes to 0 of the function evaluated at x plus h, but in this case it's going to be t plus h because our independent variable is a t. So it's g evaluated at t plus h minus g evaluated at t all over h. Okay, and we have to find the limit of that as h goes to 0. So let's find g evaluated at t plus h. Well, if I plug a number in for g, what it does, the output is going to give me 1 over that number squared. So if you write this as a shell, this is what that function does to any number you plug into it. And when the number we're plugging into it is t plus h, so it's just going to do this. It's going to say 1 over whatever you plug into it squared, okay? Minus g of t, which is just 1 over t squared. And then all of that's divided by h. Okay, so let's try to evaluate this limit using direct substitution. Okay, when I plug a 0 in for h, I get 1 over t squared minus 1 over t squared, so this is 0. And then, of course, the bottom is 0, and so it's indeterminate. So we're going to have to change the form. And I think the key to changing the form here is to make sure that we combine these two fractions on top. And so it looks like we're probably going to need a common denominator. Okay, and I think you can see that t plus h squared is one factor that appears here, but then you also have a t squared factor over here. And so the common denominator would be both of those factors multiplied together. Okay, and I'm going to put the t squared in front. The order doesn't matter in which you multiply. It just looks a little nicer if you put it in front. Okay, so that's my common denominator. And then I'm going to force in the factors that I'm missing for both of these fractions. Okay, so here I'm missing a t squared. So I'm just going to multiply this by t squared over t squared. Okay, this one's missing t plus h squared. So I'm just going to multiply it on top and bottom by that. Okay, now remember these are equal to 1, so it's okay to multiply these by 1 because it doesn't change the value of those fractions. Okay, so then look, we're left with t squared over this common denominator. And then over here, we're left with t plus h squared over this common denominator. And then all of that is divided by h. And then we have to find the limit of that as h goes to 0. Okay, but now that we have a common denominator, I can subtract the tops here. So you get t squared minus t plus h squared all over the common denominator. Okay, and I'm going to go ahead and FOIL this out on the side, and then once I figure out what it is, I'm going to go ahead and plug it in here. Okay, and then all of this is divided by h, and then of course we still have to find the limit of that as h goes to 0. So on the side, let's figure out what t plus h squared would be. Now of course you have to multiply this by itself, so that means you have to FOIL this out. And so you get t squared, and then you get t times h, but then you get h times t, which is the same as t times h. The order in which you multiply doesn't matter. And so you can write that as 2th. So that's your middle term. Okay, and then the last term, of course, will be h times h, just h squared. Okay, so that's what we get when we FOIL this out. And then let's go ahead and distribute the minus sign. So each one of these terms will be now negative. After you distribute that minus sign. And then notice that you do get some cancellations here, right? T squared minus t squared, that cancels out. And that leaves you with negative 2th minus h squared all over your common denominator. Okay, and then don't forget you're dividing this by h, and then finding the limit of it as h goes to 0. Okay. So you may want to try direct substitution again, but you're still going to get indeterminate because we haven't really canceled anything yet. You really need to cancel something out to make this determinable. And so I think what we need to do here is notice at this top piece right here, you can factor an h out of this. And that's important because I want it to cancel with this h on the bottom. So let's factor this h out of the top. In fact, let's just factor out a minus h just to get rid of this minus sign here. So that's going to leave us with 2t plus an h. Okay, all over the common denominator. And then divided by this h. And I'm going to write this as h divided by 1, which is still equal to h. But the reason I'm doing that is because when you have a fraction divided by another fraction, you can flip and multiply. Okay. And so let's go ahead and do that. So I'm going to flip this fraction and multiply by it. And when I flip it, I get 1 over h. Okay, so I'm going to multiply this top fraction by 1 over h. Okay, so again, flipping this, I get 1 over h, and then I'm going to multiply by it. And then notice that these h's cancel out, right? You have 1 on top and 1 on the bottom, so those cancel out. And now we're left with this. And now when we try, so now that I have cancellation here, right? Notice before I cancel this, I do get 0 over 0 when I try direct substitution. But when I cancel those out and try direct substitution now, on top here, I get 2t, so this is getting closer to 2t as h is going to 0. And on the bottom, this is getting closer to 0, so this is getting closer to t squared times t squared, which is t to the 4th power. Okay, so that's the limit of this function as h goes to 0. And notice here that one of the t's cancels, so you could actually write this as t, or 2 over t cubed. Okay, so that's our derivative. That's g prime of t. Now again, what does derivative tell us? It tells us several things. This function tells us the instantaneous rate of change in this function at any t. It tells us the slope of the tangent line to this function at any point t. And the derivative can also be used, of course, to evaluate the derivative at a specific t value. Okay, so we've looked at a couple of examples here. If you are trying to find a derivative that has a square root in it, you probably need to multiply by the conjugate to make the limit determinable. If you have a function which has a fraction in it and you're trying to find the derivative of something that's a fraction, which we call a rational expression, then you're probably going to need to get a common denominator for that fraction, because both of these will end up being fractions on top. Okay, so I think you need to keep that in mind. Square roots, you're probably going to have to multiply by conjugates. If you're dealing with rational expressions, you're probably going to have to find a common denominator in order to evaluate this limit. Okay, so I hope you found this video helpful. Thank you for watching. Bye-bye.